A 12-kilogram object is moved from Earth to the Moon. So what happens to its mass and its weight? Today we're cracking the code on a Cambridge IGCSE 0625 physics trap that catches thousands of students every single year. Get this wrong, and it's not just a dropped mark. It's a fundamental error that will literally crash your grade boundary.
Let's dive right into this with a three-doors scenario. Picture this. You're sitting in the exam hall, staring down this exact question. You've got three doors, or three ways, to answer. Door 1, you assume both mass and weight drop. Door 2, you assume they both stay exactly the same. And door 3, you treat them as completely independent properties. Only one of these doors saves you from a massive loss of marks, and honestly, it's the one most students fail to open.
The painful mistake learners make, the reason standard revision just falls flat, is thinking mass and weight are exactly the same thing. I mean, in everyday life, we use these words interchangeably, right? You might say, oh, I weigh 60 kilograms. But in the Cambridge physics universe, saying that is a massive pitfall. If you carry that everyday assumption into your exam, the examiner's red pen is coming out instantly.
Let's break down the critical difference we need to lock down right now. Mass is simply the constant amount of matter in an object. It's totally independent of the Earth. It does not change, no matter where you are in the universe. Weight, on the other hand, is a completely different beast. Weight is a vector quantity, meaning it has both magnitude and direction, and it's the direct result of a gravitational field acting on that mass. Because weight is a force, it absolutely must be measured in newtons, never, ever in kilograms.
So, the crucial point is understanding how these two actually connect on our home planet. On most of the Earth's surface, the weight of an object with a mass of exactly 1 kilogram is 9.8 newtons. Now, for Cambridge exams, this 9.8 is often generously rounded to 10, just to make your calculations a bit smoother. This means a mass of 2 kilograms has a weight of 20 newtons, 3 kilograms is 30 newtons, and you get the idea.
But why does this actually happen? Well, it's because gravity is an action at a distance force. It pulls objects through space without any physical contact required. Think about it. When you drop a pen, nothing is physically pulling it down, yet it accelerates straight toward the floor. It behaves exactly like magnetic forces pulling magnets together or electric forces acting between charges. The Earth is surrounded by this invisible gravitational field, exerting a continuous force on any mass caught inside it.
When we talk about how strong that field is, we use a very specific definition. The exact phrasing examiners are hunting for is force per unit mass. That is the definition of gravitational field strength. And because it's a force acting in a specific downward direction towards the center of a mass, like the Earth, gravitational field strength is a vector. It has both a size and a direction. Remembering this exact wording is a quick win that easily secures those definition marks.
Let's see how this builds into one of the most vital equations in your physics toolkit. We start with Newton's second law. Force equals mass times acceleration, or F equals ma. Now, because weight is just the force of gravity, we swap the F for W. And because the acceleration is caused by gravity, we swap the A for G. This really elegant substitution leaves us with the final examiner equation, W equals mg. This proves mathematically that weight is simply a force, and forces are measured in newtons.
Now, in just a moment, I'm going to show you the examiner clue that changes our initial moon answer completely. It's the exact phrasing that elevates a standard answer into a top-band answer. But first, you need the framework that makes this clue completely obvious. And that starts with understanding the open loop of our equation. If we take W equals mg and rearrange it, we get G equals W divided by m. This beautifully reflects our definition from earlier. Gravity, G, is the weight, W, which is the force, per unit of mass, m.
Time for an interactive challenge straight from the Cambridge text to test this framework. I want you to pause the explainer right now. Grab a piece of paper and calculate the weights for these three masses. A, 100 grams, B, 5 kilograms, and C, 50 grams. Assume the Earth's gravitational field strength, G, is 10 newtons per kilogram. Go ahead, pause now, and let's see if you can avoid a classic exam error.
Okay, welcome back. Did you get 1 newton, 50 newtons, and 0.5 newtons? The most common pitfall here isn't the multiplication itself, it's forgetting to convert your grams into kilograms first. The formula W equals mg only works when mass is in standard SI units, which is kilograms. 100 grams is 0.1 kilograms, 50 grams is 0.05 kilograms. If you just multiplied 100 by 10 and wrote down 1,000 newtons, you just fell for the ultimate examiner illusion. always, always convert to kilograms.
Now, consider this fascinating real-world anomaly. Because the Earth isn't a perfect sphere, it actually bulges at the equator and is slightly flatter at the poles. Your distance from the center of the Earth changes depending on where you stand. And because gravity is an action at a distance force that gets weaker with distance, your weight actually fluctuates. You literally weigh slightly more standing at the North Pole than you do on the equator. Your mass hasn't changed a single bit, but the gravitational force acting on you absolutely has.
Returning to our initial moon question, let's look at a classic flawed student answer. The 12 kg mass weighs 12 kg on Earth and 2 kg on the moon. This answer is an absolute disaster for your grade. It completely ignores everything we've just discussed. It uses kilograms for weight instead of newtons, and it assumes mass somehow changes based on location. This answer gets 0 method marks because it shows a fundamental misunderstanding of core physics concepts.
To fix this completely, we're going to apply our mark magnet framework. This ensures we hit every single scientific reasoning point the examiner's red pen is actively looking for. Step 1, state the concepts that mass is constant. Step 2, provide the evidence, noting the moon's gravity is 1/6 of Earth's. Step 3, show your reasoning by calculating W equals mg separately for both locations. And finally, Step 4, use perfect examiner wording by stating your final vector values explicitly in newtons.
So, applying that framework, here is your top and corrected answer. First, we clearly state mass remains 12 kilograms everywhere. Boom, concept mark secured. Next, Earth weight, 12 kilograms multiplied by 10 newtons per kilogram equals 120 newtons. Calculation and unit marks secured. Finally, moon weight. We take that 120 newtons and divide it by 6, giving us 20 newtons. This perfect answer cleanly separates the constant mass from the gravity-dependent weight, guaranteeing you every single mark available for this question.
You've successfully locked down the core concepts of mass, weight, and gravity. You know how to use W equals mg, and you know the units. But this raises a critical question. If weight is just a downward force that changes based on gravitational fields, how do we evaluate complex anomalies in the exam when multiple forces are acting on an object at the exact same time? What happens when we introduce tension, friction, or air resistance into the mix? This introduces an entirely new, higher-level layer of physics you need to master to secure those top grades. To ensure you don't lose marks on these complex, multi-force anomalies, you must understand how examiners grade these high-level questions. But before we move on, remember this. Your mass grounds you to reality, but it's gravity that gives you weight in the universe. Are you ready to see what happens when the universe pushes back? Door 2 opens right now in our next explainer. You must dive into our next session covering the top-band evaluation framework for forces. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click the explainer on your screen right now, and I will see you there to master complex forces.